Okay, so last class I introduced you guys to the chain rule, and we focused on looking at more complicated functions as composition of functions, so we can learn how to apply the chain rule. So today, we're going to go ahead and apply that chain rule. So let's say we have y equals sine of x squared, and we want to find y prime, the derivative of y, or dy dx. So when I look at this function, thinking of compositions, I see this as y is equal to the sine of u, where u is just equal to x squared. So if I take the derivative of y with respect to u in that first equation, well, we learned that that's the cosine of u. In the second equation, if I take the derivative of u with respect to x, well, the derivative of x squared is 2x because of the power rule that we learned. So therefore, if I want to find dy dx, which is the derivative of y, then I'm going to have to do the derivative of y with respect to u times the derivative of u with respect to x, which I've just calculated. So dy du was the cosine of u, and du dx was 2x. And now u is just a temporary variable. Go back up here. Remember what u is equal to. U just represents x squared. So I'm going to go ahead and replace u with x squared. And I get my final answer, cosine of x squared times 2x. And I'm going to put the 2x in front of the cosine, but it doesn't really matter. And so that's my derivative. Now at first that may seem a little awkward, cumbersome, tedious, but you'll get the idea. So let's do another one. Let's find the derivative for y equal 3x minus 4 quantity squared. So let's start off with, I look at y and I see that as something squared. So y is equal to u squared. And then the something, that u, is really equal to 3x minus 4. But first I have to take care of the derivative of something squared. So the derivative of y with respect to u is 2u. Now in the next equation, if I want to take the derivative of u with respect to x, well, that's just going to be 3. And the derivative of 4 is 0, so my derivative is just the constant 3. So now when I want to find dy dx, I'm going to have to multiply dy du, which is 2u, times du dx, which is 3. So I get 6 times u. But remember, u was just a temporary variable, so I'm going to replace it with 3x minus 4. And so I get my final answer for the derivative of this function is going to be 6 times the quantity 3x minus 4. Now if you want, you can distribute that. You don't have to. But either answer would be correct. And y do extra work, so let's just leave it like that. Now, if you don't really think that that works, or you're not quite sure, we could have expanded this right off the bat and made it 9x squared minus 24x plus 16. And when you take the derivative of that, we use the power rule. 2 times 9 is 18, and then x to the first power. The derivative of 24x is just 24, and the derivative of 16 is 0. And oh my gosh, we got the right answer. Okay, let's try and do all this work without writing all this extra, let u equal this, and dy du, and then going ahead and doing all that stuff. I think we can just jump right to the answer from the start. So let's look at some more examples. When I'm taking the derivative of a composition of functions, I'm going to take the derivative of the outside function first, and then multiply that by the derivative of the inside function. So here's what I mean by that. Okay, when I look at this, I see two functions. I see the square root of something, and then I see x cubed minus 2x. So to find this derivative, first I'm going to take the derivative of the square root of something. Think of that as like square root of x, or x to the 1/2 power. So that's going to be 1/2 times something to the negative 1/2. And that something is x cubed minus 2x. Okay, now I've taken care of the outside function, the square root function. Now let's take the derivative of the inside function, which is x cubed minus 2x. And the derivative of that is 3x squared minus 2. So final answer, I would probably write it this way. But there's many different forms. And if you leave it actually the way I had it before, that would be fine as well. Clear as mud. Let's do another one. All right, let's do the derivative of sine squared of x. Not sine of x squared, sine squared of x. So when I look at this, first I see something squared. How do you do the derivative of something squared? Well, we do 2 times something to the first power. Okay, I've taken care of the squared part. Now I have to multiply my answer times the derivative of the other part, which is sine of x. And the derivative of that is cosine of x. We're done. Now you may recognize that from the double angle formula, and that happens to be the same thing as the sine of 2x. So if you wanted to be really clever, you could write it like that. Either one's fine. Okay, well, let's back up. So what I would recommend now is for you to hit pause or stop and practice the chain rule in section 15b.2, page 366, numbers 2 through 4. Okay, you've done the chain rule. So now let's look at two more rules called the product rule and quotient rule. And with these tools and the power rule and the chain rule, you should be able to calculate derivatives of most functions that you'll come across. All right, so if you see a function as the product of two functions, to find the derivative, you're going to have to find the derivative of the first function, that's u prime of x, and multiply that by the second function. And then we're going to add to that whatever the first function was times the derivative of the second function. So we're kind of taking turns. First we're going to figure out the derivative of the first function, and then we're going to figure out the derivative of the second function. A shorter way of writing this, instead of using all the function notation with the parentheses and the x's, is you can think of it this way. The derivative of u times v is u prime v plus uv prime. And that's our product rule. Well, if we have a product rule, of course we're going to have a quotient rule. So if you're dealing with a function that's the quotient of two functions, then to find the derivative looks kind of complicated, but it's really not that bad. So we have a top function and we have a bottom function. Don't think of that b of x as something to the negative first power. Just treat that as a function by itself. It's not part of a fraction. Think of these as two separate functions. All right, to find the derivative of this, we're going to take the derivative of the top function and multiply it by the bottom, and then minus, and then we're going to take the top function and multiply that times the derivative of the bottom function, and then all of that is going to go over the bottom function to the second power. Seems kind of complicated. Let's rewrite it without all the x's. The derivative of u over v is going to be u prime v minus uv prime over v squared. There's your quotient rule. Okay, so if that seems a little confusing, let's just do a couple of examples, and then I think you'll see it's actually quite easy to do. So, let's find the derivative for y equal x squared times the square root of 8 minus x. We're multiplying two functions here. So, I'm going to write this over here. It's going to be u prime v plus uv prime. That's going to be what y prime is equal to. So y prime is going to equal the derivative of the first function, the derivative of x squared is 2x, times the second function, which is the square root of 8, x minus 8. Plus, now I'm going to write the first function and multiply it times the derivative of the second function. Now the derivative of the square root of something, we've done enough of these, so hopefully you realize how I'm coming up with this answer. It's 1/2 times x minus 8 to the negative 1/2 power, which I'll write as that fraction. So final answer, there's really not a lot we can do to simplify this. So I'm going to write it as this. Now the nice thing about doing derivatives, I guess we could always graph the original function, or actually we could graph the original function in y1. We could put in y2 the derivative of y1, and then in y3 we could put our answer and see if y2 and y3 are the same graph. But that sometimes would take a lot of time, especially entering some of these complicated derivatives. All right, let's try another one. Let's find the derivative for y equal x cubed times the quantity 1 minus 3x quantity squared. So we'll work through this a little more quickly. So dy dx is going to equal the derivative of the first function times the second function plus the first function times the derivative of the second function. Wait a minute. This second function is going to require the chain rule. So first I take the derivative of something squared, and that's 2 times something to the first, and then times the derivative of that inside function, 1 minus 3x, and that's a negative 3. So the entire derivative of 1 minus 3x quantity squared is 2 times 1 minus 3x to the first times negative 3. So my final answer here, I have 3x squared, 1 minus 3x quantity squared, minus 6x cubed, 1 minus 3x. I guess we could factor a 1 minus 3x out of both of those terms, but it's not going to simplify anything or cancel anything out. So that's fine, we can leave it like that. All right, let's try a quotient rule. So to find y prime, or dy dx, let's remember how that worked. That was u prime v minus uv prime over v squared. So the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay. So remember, the u is equal to x squared. The v is equal to 2x plus 3. Not 1 over 2x plus 3. It's just 2x plus 3. So u prime is 2x, and v prime is 2. Okay, we can clean this up a little bit. If I distribute in the numerator, 2x times 2x is 4x squared. 2x times 3 is 6x. And then I have minus a 2x squared. In the denominator, I'm not going to square that. I'll just leave it condensed like that. And now on the top, I do have like terms. So 4x squared minus 2x squared I can combine. And that'll give me a positive 2x squared plus 6x. We could factor a 2x out of the top, and we'd have an x plus 3, but that wouldn't help us cancel anything, so that's good. All right, let's try one more. So here, u is equal to the square root of x, and the derivative of that is 1 over 2 root x. And the v is equal to x squared plus 1, and the derivative of that is 2x. So the derivative of this is going to be u prime v minus uv prime over v squared. So let's just plug in all those values. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Now this one looks a little complicated. I guess we have a complex fraction. Maybe we should do some work and combine stuff. So there's a few routes you could go with this. You want to keep your life simple. You could change 1 over 2 root x as 0.5 x to the negative 1/2 power x squared plus 1. Guess we could do that. And then with the second term there, x to the 1/2 times x to the 1, that's really 2x to the 3/2 power. So that would be one way you could write it. Now if you jot that down, great. I'm going to erase that. So you got a second, pause. Too late, gone. Okay, if I stick to my complex fraction, I have x squared plus 1 over 2 root x minus 2x to the 3/2 over 1 all over x squared plus 1 squared. Now, I'm going to have to get a common denominator, I guess, so I need to multiply this by 2 root x, or 2x to the 1/2. So that's going to simplify. I'm going to have an x squared plus 1 minus 4x squared, x to the 3/2 times x to the 1/2, that's x to the 4/2, which is x squared, over my common denominator, over my denominator. But remember, dividing by x squared plus 1 quantity squared is the same as multiplying by 1 over that. So final answer, and if I made any mistakes in simplifying that, since I'm on video, nobody can tell me I made a mistake, and we'll just say that's right. Okay, but you have the idea between the product rule and the quotient rule. The chain rule takes a little more practice, I think. But 15C, 15D are your other sets of problems, and those deal with the product and the quotient rule. Hopefully you'll be able to get a good start on the homework, and I'll answer more questions in the next class. Thanks.